sparse signal recovery from phase of complex random measurements.
Okay, thank you, Charles, for this very nice introduction. First, I'd like to thank the organizer for this invitation, for this virtual meeting about AI for signal and image processing. As you may see, the title of my talk is about yet another story of compressive sensing, and in particular, the context where you do complex compressive sensing with complex sensing matrices, and you are interested into recovering a signal only from the phase of those observations. So to be totally honest with you, this talk is actually totally 0% deep learning, so it's totally free of AI somehow, and I'm sorry about that. It's a purely classical compressive sensing. However, it is slightly connected, at least to the topic of today, in the following sense, is the fact that here is an example of a nonlinear compressive sensing model, of a nonlinear sensing model, for which anyway, up to a global amplitude of the signal, it's possible to totally recover the signal of interest. So it's a weak link with somehow some of the topics you may see nowadays in the context of a nonlinear neural network, where anyway you can reconstruct your data at the output of the neural network or to classify them. So it's a bit related to that, but it's not totally connected to the theme of this meeting. Anyway, I'm open to any questions related to this talk, and in particular to any connection you will see between what I'm going to explain today and some applications in the context of spectral sensing, so any sensing using Fourier measurement, for instance, and for some reasons that are going to be clear in a moment. So let's start this presentation with a bit of history, and in particular with one experiment that was designed by Alan Oppenheim and Lim in '81. And they were interested into the following question. So they were interested into knowing what was the most important between the spectral amplitude and the spectral phase of signals. And to answer to these questions, at least experimentally, they designed this experiment that I've reproduced here with another image that the one they used initially. So they just considered the Fourier, the two-dimensional discrete Fourier transform, here represented by this operator F, and they applied it to an image with a certain resolution. And then they considered two possible scenarios. The first one was simply to recover that image from only the amplitude of the spectral content, so simply killing the phase with the keeping only the absolute value of the Fourier component and inversing the Fourier transform. And you see here that actually you just get garbage. You don't see anything related to the initial image there. However, if you consider the second scenario, where you keep the phase of the spectral domain by simply renormalizing the Fourier content and inverting the Fourier transform, then you see that somehow some of the edges have been preserved in the operation, and it's not perfect, but at least the informative content is better in the second scenario than in this scenario here, which is not interesting. So I do not say that phase retrieval is not working, so don't misinterpret what I'm saying here. It's just that in that particular and specific context, you do not see anything here. So this is the experiment that Oppenheim did, and with his collaborator, they wanted to do better than the reconstruction, which is here. And to do that, what they do is simply to consider another algorithm than this linear transformation, and they consider an algorithm that was already well known in the literature, which is the alternate projection onto convex sets, in order to estimate the initial image up to a global amplitude, because of course, keeping the phase of the spectral content is totally invariant to any rescaling by some factor, positive factor of the image. So what they did is to first define two convex sets. And the first is simply associated with the set of all images having the same observations. That is, if you really reobserve the spectral phases, they are the same as the phases you have stored in memory. And actually, I should be slightly more careful here. When I speak of the phase, actually, I speak of the phasor, that is the imaginary exponential of the phase. So I will often just consider one for the other. And the second convex set is the set of all images that are supported on a given subset of the plane. So possibly the image is bigger with 0 outside, but I know that the content is on a certain set omega. And so by considering these two sets, OpenEye just run this iteration, which is just the standard POX algorithm, not related to phase-only compressive sensing. So it's just the same acronym is different, where they alternate from an initialization point here between two orthogonal projections, and they are very easy to compute actually, between the set of consistent images with the same phases and the set of images that are supported on the same domain. And so they repeated that operation until convergences. And then if you do yourself this experiment, and actually I will give you a link at the end of the presentation where you can download some demo if you want to convince yourself that this is actually working. If you do that, and if your set omega is simply the domain of the image, and you extend the image with 0 padding in order to have a larger domain so that omega makes sense. If you run this POX algorithm, after a few number of iterations, very rapidly, you see that you recover something that is almost as close, almost the same as the original image here. So of course, the amplitude is lost, but you can always rescale the two so that you see that the image is about the same. And you can even study the evolution of the signal to noise ratio as a metric of quality, the evolution of the SNR in function of the oversampling ratio between that is the total number of observations that are related to the dimension here of the full domain with the 0 padded values and the total number of pixels you had initially in your image. So it's a measure somehow of the ratio between the actual number of observations you have in your problem in that specific scenario and the initial dimension of your image. And if you do so, you see that very quickly, starting from a setting where you don't have enough observations, enough measurements, enough pixels in this case, you quickly increase the quality of your reconstruction with levels that are very interesting to have some images that are very close to the original. Okay, so why is this experiment interesting? Because outside of the theoretical question and the interesting aspect of this experiment, of course, there are many applications nowadays that rely on spectral content and Fourier transform. And so this is the case. I don't have to tell you that. There are many experts here today that this is the case in magnetic resonance imaging, but also for radar systems. Any interferometric measurement actually relies on some Fourier transform somewhere. This is the case also for aperture synthesis in radio interferometry. So there are many applications that relies on the Fourier transform, on the spectral content of some image or objects. And for those applications, there are some big challenges because for all of them, it is better and better to reach higher resolution images. And because you want to reach such a resolution, you need to ask more to the devices that does the acquisition. And so you have massive data streams that goes between the sensors you use, for instance, the antennas you have in a radio telescope here, an array of radio telescope, and the server that eventually will do the reconstruction. So you have those massive data streams. And because they are massive, you need to compress that information for subsequent reconstruction process. But of course, you need to have a compression which is friendly with the reconstruction. You have to be extremely careful to not compress the measurements in a way that will just destroy your ability to reconstruct the image. And moreover, you may have applications where you have very large magnitude variations in the spectral domain, but also in the spatial domain of the image you are interested into. And because of these very large variations, you have to be very careful to the way you are going to compress information, because you could introduce some biases, some strong distortion for very small amplitudes, part of the measurement compared to large magnitudes parts. So here, thanks to this observation by Oppenheim, we have the right to consider the question of just keeping the phase and not the amplitude of those observations. Because if you are capable to have an approach where only thanks to the phase you can reconstruct such images, then possibly, if your approach is sufficiently robust, you may even quantize the phases with a certain number of bits, with a certain resolution, and still obtain something which is good, sufficiently good for the reconstruction, without to have all those sensitivity to the large magnitude effect I mentioned earlier. So here in this talk, I will only focus on the context of complex compressive sensing, and in particular, in the very restricted case of Gaussian sensing matrices, even if I have some numerical results later, I will show for partial Fourier transform, as a way to enter into this model and to see if we can characterize everything theoretically or not. And yeah, and so as I mentioned, the interest of that is that later possibly you can quantize the spectral phase. Okay, so I need now to reintroduce a few concepts of complex compressive sensing. I know that a certain number of you are very familiar with that, but I prefer to stabilize our knowledge around this topic because I will rely on that for the phase-only compressive sensing. And so the first thing I'm going to do is to consider this linear model here. So far it's just the linear compressive sensing, where I have M observations that are recorded into a measurement vector Y, obtained thanks to this sensing model where I have a low complexity vector X. It could be a sparse vector in some basis, or a low rank matrix, provided that you turn it into a big vector. It could be many other kind of models, provided that they are all of low complexity, meaning that they occupy a very small domain in your high dimensional space with n dimensions, and actually 2n because you consider the set of complex signals. And the matrix here is considered to be complex, and I allow to have a bit of noise in this model with bounded energy here. So in this context, what tells us the theory of compressive sensing is that despite the fact that M is smaller than N, provided that M is bigger than the typical dimension of the informative content of the signal X, then if A is random, you can recover exactly X in absence of noise. And if there is noise, then you can show that the system is actually robust to noise. And I'm going to develop that in the next slides. So this is, of course, the discovery of Candes, Tao, Dono, and this is summarized also in the book of Simon Foucault and Holger Roth. So this is very well known. And one of the ways you can use to show that, there are other ways, like the null space property, but if you consider the restricted isometry property as a way to show that your sensing matrix is sufficiently well conditioned, because there is always a question of conditioning if you want to invert something somehow. The property you need here is that RIP property, which tells you that if A is random, that tells you that the norm, the length of a vector V observed or mapped by the sensing matrix A is very close to the length of the initial vector. So this property amounts to that. And it happens that if you generate such a matrix randomly, for instance, with a complex Gaussian sensing model, which is here represented in that formula up to a normalization, then you have exactly what you wanted from the beginning. That is the fact that this matrix will be RIP, provided that M is bigger than something that grows like the dimension of your model, which is here the amount of non-zero coefficients you have in V, that is the sparsity level K. So provided that M is bigger than that, up to other factors that are here, you can show that with very high probability for any K-sparse vector V, this RIP matrix, this RIP property will hold. So that's the principle of this RIP property, and which is good news because it means that if M is smaller than N, but anyway, a few multiples of K, you can hope to reconstruct your signal. And so in essence, the reason why it works is simply because thanks to the RIP property, you have a way to measure the distance between your true signal, even if you don't know it, and any other estimate, thanks to the observation process, because if Y is your observations, then if you take any candidate U, which is K-sparse, and if the matrix is 2K RIP, then the distance, which is here fidelity term, the distance between Y and AU is just very similar to, up to some distortion, to the distance you have initially between X and U. And this is really the point that is used by many algorithms to, starting from the measurements, obtaining some very good estimate. So somehow it's a way to say that the matrix IA is invertible over the set of K-sparse vectors. And so to finish this introduction to compressive sensing, the most important, one of the most important things is, which can be characterized as one of the fundamental theorems of compressive sensing somehow, is the fact that there exists an algorithm, actually a program, that allows you to reconstruct your signal X, or to estimate it. And this program works as soon as the matrix A is RIP 2K, so RIP over 2K sparse vectors with some delta that should not be too big, smaller than this quantity actually, which is tight, thanks to the discovery of K and Zhang. And so provided that you minimize the L1 norm as a proxy to the measure of sparsity, and subject to the fact that you want to be very close to what you have observed in that sense here, then the error you commit between X and the estimate is bounded by two terms. One, which is your deviation to the model, which is exactly 0 if X happens to be exactly K-sparse here. And there are other models for other low complexity domain for X, but this is the one for the set of K-sparse vectors. And another term, which is the term coming from the amount of noise, which means that if X is exactly K-sparse, this term vanishes. And if there is no noise, this term is also equal to 0, meaning that you can exactly recover X from the output of this program here. Program that can be solved with many different toolboxes. And of course, there are many other algorithms that allows you to recover a good estimate. Some are based on greedy methods. Charles is a very big expert on that, for instance. And it's really important to know that it's just one facet of the thing you can do in order to estimate your vector X. So that's it for the introduction to compressive sensing. And now I need to jump to the nonlinear model. And so inspired by the work of Oppenheim and also by the work of Petros Boufounos, who was up to my knowledge, he was the first to consider the context of phase-only compressive sensing. Now you can really leverage the fact that you have complex observations in AX and formulate this nonlinear model where you keep only the phase thanks to this sign operator in the complex domain that just kills the amplitude here. And you keep the phasors, here the phasors in blue, because this operator is applied component-wise onto the output of AX. And so, and you allow also a bit of noise, but I will, for some reasons that will become clear in a moment, I will only consider bound on that noise in L infinite sense. So this is the model I want to consider, and I restrict myself for some reason I'm going to explain in the next slide to the context where X is real, despite the fact that the matrix A is complex and K sparse and not a low complexity vector in any domain. I just, for the sake of simplicity, I just focus here on the set of K sparse signals. So some key observations. First, as for the previous experiment, of course, the system is totally invariant to any rescaling of the initial signal X with some positive constant and real, because, of course, the sign operator will just kill any rescaling of the amplitude, and because the sensing is linear here. Another observation is that in the context where both A and X are not complex but both real, then it happens that the sensing vector here, which is non-linearly obtained, becomes totally real, and actually it will only take two values, plus and minus 1. And this is known in the literature as one-bit compressive sensing, for which there is somehow a negative result. So there are positive results, of course, but the negative here result I'm referring to here is the fact that it's impossible to get an estimate of X with an error that will decay faster than 1 over m if m, the number of measurements, increases. So this is known in the literature. And so the question we will pursue in the following is whether or not the same lower bound holds in the context of phase-only compressive sensing. And spoiler alert, no. So why am I considering a real signal and not a complex signal X? Because at least formally here, you can always rewrite your problem from a context where you have a vector X, which is complex, to a context where you have a vector which is real. It's always possible to rewrite everything here if you expand the dimension of your problem by a factor 2, and if you developed a new vector here that will just concatenate the real and the imaginary part of your signal X. And you have just to redefine a new matrix here from the matrix A. And then you can consider that your sensing model is equivalent to a sensing model where even if X initially is complex, it's associated with another vector that is totally real in a 2 times bigger domain. You need to pay attention anyway to this reformulation, because saying that a vector X is sparse in the complex domain is not exactly the same as saying that X bar here is sparse. And you have to pay attention to the way you define the sparsity. And in particular, something that is sparse here will become group sparse. You need to consider simultaneously the real and the imaginary part here for their component to have exactly the same meaning. But this is something, this is the limitation of this rewriting. And as I mentioned, for the sake of simplicity, the second point is that I will only focus here in the case on the case of sparse vectors. But actually, everything I'm going to explain can be extended, and it is done in the related paper, to low complexity signals, provided that you can bound their dimension somehow, like, for instance, low rank matrices. Okay, so let's turn now to the theory that allows us to do phase-only compressive sensing, and we simplify again further the model by just considering that it is noiseless. And the way I'm going to tackle this problem is by turning this nonlinear model into a linear one. And to do so, the very first thing I'm going to do is first to realize that I can leverage the rescaling effect, the fact that we have lost the amplitude of the signal. And so I have the right to take exactly the normalization I want for my signal. And in particular, I have the right to define a new signal X star here, which is just parallel to X up to this normalization constant here, where the value of kappa is this quantity. And the reason why I'm using this normalization constant here is that first, if I consider now the L1 norm, which is an important norm for the rest of the analysis, the L1 norm of AX star, it is going to be always the same value. So it's thanks to this normalization. And because of that, I know that any estimate I'd like to get will have to respect this, basically. So the rationale of this constant now here is that first, it's very useful for our proofs, but this is not very useful for you. And the second point is that it is possible to intuitively know why it's an interesting constant, because since you know that you can compute, it's a very well-known fact in statistics that the expectation of the absolute value of a Gaussian random variable is just equal to kappa, the same kappa that is here. Then on average, you can show that the L2 norm is very close, the L2 norm of X star is very close to unity. And so it's a bit equivalent, imposing this is a bit equivalent to stay on the surface of a sphere for the set of vectors we want to reconstruct, which makes sense because somehow we don't have any amplitude, so why not staying on the sphere? Okay. So this being said, now I can just develop the different constraints I want to use. And the very first one is a constraint which is actually totally deduced from the normalization I have introduced earlier. So if you consider a vector u and you plug it into this constraint here, so you take the vector z that contains all your phasor information, all the phases of AX star, which is the same as the phases of AX because of the sign operator, then this quantity here, the scalar product you have there, will just be tantamount to compute the L1 norm of AX star in the specific case where X star is, where U, is equal to X star. And so for any other estimate, it makes sense to impose that I want this to be equal to the same value I had when I consider U equal to X star, that is kappa times square root of n. And if I message a bit this constraint here, is just equivalent to project U onto this vector in blue. And so this is nothing but a hyperplane, which is with an offset of 1 that I consider through this constraint. So it's totally linear here. And the second constraint I'm going to consider is a convex one, which is somehow related to the way I've defined this one. I just built here a diagonal matrix where I insert Z onto the diagonal. And if I apply that to the vector AU, in the very specific case where U is again equal to X star, I will see that all the component of the vector I get at the output of this product will be equivalent to the absolute value of any of the component of AX star from 1 to m. And so everybody there is positive. And so it makes sense to say that if I want a reliable estimate, I must impose also the fact that the vector here for any estimate U should be real and also positive. And actually the positivity constraint, I'm going to skip it in order to relax my problem. And by removing it, just imposing the fact that this guy here is real is equivalent to say that its imaginary part must be equal to 0, which is also a linear constraint. And so in the context where, as I assume at the beginning that U is real, up to this recasting I formulated, then the imaginary part of this guy being equal to 0, I can just reformulate that as a big matrix applied to U that must be equal to 0. And this big matrix is simply this thing here. If you trust me on the development of that, it's just one line, where you just have a mix between A and Z. And so as soon as you have the vector HZU here, you know that it must be equal to 0. And moreover, the normalization will just split in two constraints, the real and the imaginary part, where the real is equal to 1 and the imaginary part is equal to 0. So in summary of all this, the point is that you can gather the blue vector alpha and the matrix, the big matrix HZ into a big matrix here. And if I gather everything and if I apply that to a vector U, I know that because of the normalization constraint, the first component, which is related to this blue vector here, should be equal to 1, and all the others should be equal to 0. But this is nothing but a linear constraint that is very similar to compressive sensing in general, to linear compressive sensing. And so once I realize this, I can just ask the question of the possibility to estimate X star from the observations that are here equal to this vector E1 defined by this. And so the point here is simply to use this linear formulation to inject it into this basis pursuit program, which is just basis pursuit denoise when there is no noise, where now the sensing matrix A is replaced by AZ, and the measurement vector Z or Y is replaced by this vector E1 here. And so to be sure that you have some guarantees on the estimate there, the question to ask is whether or not AZ respects the RIP property. So I'm not going to develop the proof of that. I'm just going to give you the intuition of why it can be possible to reach the RIP property with high probability for AZ. And the first thing to realize to show that is that AZ again is developed like this triplet of vectors and metrics. And if you apply that to a sparse vector V and you compute the L2 norm square here, you will have two components square. And it happens that you can show that the very first component is a bit equivalent to project the vector V onto the direction of X, which is encoded actually through X star, but through alpha Z also. So this is equivalent to project V onto the direction of X. And since we know that this part should be equal to 0 if you apply Hz to X, if you apply Hz to V now, you can show that actually Hz satisfies the RIP property also, but not anywhere. It satisfies the RIP property on the set of two k-sparse signals, but not all of them, only those that are perpendicular to X. And because of that, the principle is that you can apply Pythagoras, because this thing will be equal to this projection onto the direction of X, and this thing will be equivalent to extract the component of V that is aligned with X, that is, you keep V perp, which is orthogonal to X. And so by Pythagoras, this thing is just close to the norm of V, which is precisely what you need to show that this thing is satisfies the RIP property. Okay, and then you have a theorem that is very similar to the previous one, which shows that, and this is a non-uniform result, if I fix X, then given a certain resolution delta, I can show that with high probability, provided that M is sufficiently big compared to the sparsity level, AZ will satisfy the desired RIP property, which then allows me to show that the estimate produced by the basis pursuit algorithm is a good one. It will be sufficiently close to X and possibly exactly equal to X star if I have no noise and if I know that X star is exactly k-sparse. Okay, so now it's time for a bit of simulations before to conclude. So just to show you that I'm not dreaming and all these things are actually working, let's take a Gaussian matrix here in that dimension. So I have n equal to 256 and m is a number of measurements that will range between 1 and 256. And I take just 20 sparse vectors in that domain. I will average all my results as it is traditionally done in the compressive sensing literature over a certain number of trials to have sensible curves. And I will consider, in order to get a transition curve, which measures the success of this approach, I will consider that I'm successful if the SNR of my reconstruction is higher than 60 dB. If I do that, I obtain the following interesting graph. In this graph, I have represented the recovery rate, that is the percentage of success, versus the oversampling ratio, that is the ratio between M and K, that is weirdly becoming S here, but it's the same. So the point is that I have just also plotted the curve of traditional linear compressive sensing in comparison with what I get for phase-only compressive sensing. And you see here that there is a shift on the right. So you need to ask more measurement to have a success of the phase-only compressive sensing. And somehow it makes sense because from the 2M, so from the M constraints I had in phase-only compressive sensing, M complex constraints, that is 2M real constraints, I jumped to, thanks to my recasting of all the phase-only compressive sensing into a linear context, I have jumped to a constraint that has M plus 2 equations. So I jump from 2M to M plus 2. And so the ratio between the two, when M is sufficiently big, is very close to 2, which is somehow consistent with this shift we see here. So that's it for this first simulation. And now if we dare a little bit more than simply playing with Gauss, we try Bernoulli random matrices or random partial Fourier sensing matrices, and we do observe similar transition curves. However, you have to pay attention to the fact that those two matrices are not covered by theory. First, because the Bernoulli random sensing matrices, they are known to be invalid for, they are not working in the context of one-bit compressive sensing. Moreover, which is a special case of phase-only compressive sensing. Moreover, if you play with Fourier, it's very easy to generate counterexamples of two signals, distinct signals, sparse, that will generate the same phase in the Fourier domain. And for instance, if you take just the signal X and plus a small translation of X with a multiplication by a small amplitude, it will do the job, and the two signals will have the same spectral phases. And just to finish, the very last simulation is to show the robustness with respect to noise. And now I just inject a certain noise onto my phase-only observations with a vector size, a noise which has a bounded N infinity norm with tau smaller than 2, because actually why 2? Because it's always possible to find a vector which will scramble the phases of AX at random, for which you know that you have lost completely the information about X inside. And that scrambling, you can rewrite it as the addition of a noise which has an infinity norm smaller, strictly smaller than 2 or equal to 2. And so if you do that, you have this accumulation of curves where somehow here in the color bar, you have the input SNR of your system. So blue is high SNR and red is low SNR, which is related to the value of tau. And you see that you have something very similar to the context of linear compressive sensing, where the more you have noise in your system, the lower will be your ability to reconstruct a high quality estimate of your signal X. Okay, so last slide. So some takeaway messages. So despite that, the fact that we are playing with a nonlinear sensing model, and despite the fact that we have some wrong messages coming from the theory of one-bit compressive sensing, I'm almost finished. Then in the Gauss world, at least, it's possible to do as well as linear compressive sensing up to a slight increasing of the number of measurements. And then what you can do is, of course, to reconstruct X up to an unknown amplitude. So you recover only the direction of XR. And so possibly this could lead to some interesting applications where you really need to rely on the phases, or it could be a good idea to rely on the phases of spectral information, as I mentioned in the very beginning. And so, of course, there are some open questions, like really extending everything to complex, low complexity models, because there are some details in the reformulation I mentioned at the beginning, which are still not solved. And a major thing would be to extend that theory to a broader class of sensing matrix than the Gaussian sensing model. For instance, Fourier, but with some restriction because there are some counterexamples that exist. Okay, so that's it for the presentation. I'd like to thank you again. And with this, I'd like just to conclude and tell you that if you're interested to play a little bit with the codes, you can access them on this URL here, and you have there the list of references related to my talk. Thank you very much.
Thank you very much, Laurent, for this nice presentation.